create an index to speed up the selection of data records from a table. An index can be considered to be a copy of a database table reduced to certain fields. This copy stores the data in sorted form. Sorting the data enables fast access to the records of the table, for example, using a binary search. An index contains those fields of the database table which are relevant for database queries. The index also contains a pointer from the index entry to the corresponding table entry so that all the field contents can be read.
The database optimizer decides which index on the table should be used by the database to access data records. Uses of unique index are as follows. The fields of a unique index identify each record in the table uniquely. When you insert or update table data, the system ensures that there are no duplicate entries in the database table. The performance improvements brought about by indexes strongly depend on the underlying database system. For this purpose, you can specify the database systems on which the index is created.
Table buffering increases performance when the records of the table are read. The records of a buffered table are read directly from the local buffer of the application server on which the accessing transaction is running when the table is accessed. The table buffering eliminates time-consuming database accesses. The table access performance is improved by a factor of 10 to 100. The increase in speed depends on the structure of the table and on the exact system configuration. Buffering, therefore, can greatly increase system performance. Buffered table records are stored in the main memory of the application server. If the memory is exhausted, the system discards the table record that was accessed least recently. When you enter $$TAB in the command field, the system resets the table buffers on the corresponding application server. Only use this command if there are inconsistencies in the buffer. In large systems, it can take several hours to fill the buffers. The performance is reduced during this time.
When a record of the table is accessed, the buffering type determines which records of the table are loaded into the buffer of the application server.
With full buffering, the table is either completely in the buffer or not at all. Whenever a record of the table is accessed, all of the table records are loaded into the buffer. When you decide whether to fully buffer a table, you must take the table size, the number of read accesses, and the number of write accesses into consideration. The smaller the table is, the more frequently it is read, and the less frequently it is written to, the better it is to fully buffer the table. When one record of the table is accessed, all the records whose generic key fields agree with this record are loaded into the buffer. The generic key is a left justified part of the primary table key. The generic key must be selected so that the generic areas are not too small, which would result in too many generic areas. Full buffering is preferred for the table that has few records for each generic area. If you choose a large generic key, too much data will be invalidated if there are changes to table entries, which would have a negative effect on the performance.
In single record buffering, the records that are actually accessed with select single are loaded into the buffer. Differences between single record buffering and the other buffering types are as follows. Single record buffering saves storage space in the buffer compared to generic and full buffering. The overhead for buffer administration is higher than for generic or full buffering. Considerably more database accesses are necessary to load the records than for the other buffering types. You only need one database access to load a table with full buffering, but you need several database accesses with single record buffering. Therefore, full buffering is generally preferable for small tables that are frequently accessed.
The SAP system manages and synchronizes the buffers on the individual application servers. If an application program accesses data in a table, the database interfaces determine whether this data is located in the buffer of the application server. In this case, the data is read directly from the buffer. If the data is not in the buffer of the application server, it is read directly from the database and loaded into the buffer.
As the buffers reside locally on the application servers, buffers must be synchronized after data has been modified in a buffered table. Synchronization takes place at fixed time intervals that can be set in the system profile. The corresponding parameter is RDISP/buffer time and defines the length of the interval in seconds. The value must lie between 60 and 3600. We recommend a value between 60 and 240. Assume a system with two applications. The following example shows how the local buffers of the system are synchronized. Starting situation. Neither server has accessed the records of the table SCHAR yet to fully buffer them. Therefore, the table does not yet reside in the local buffers of the two servers. Time point 1. A program running on server 1 reads records from table SCHAR on the database. Time point 2. SCHAR is fully loaded into the local buffer of server 1. The local buffer of this server is now used for access from server 1 to the data in the SCHAR table.
The next two time points of the buffer synchronization process are as follows. Time point 3. A program on server 2 accesses records in the table. Since the table does not yet reside in the local buffer of server 2, the records are read directly from the database. Time point 4. The SCHAR table is loaded into the local buffer of server 2. Therefore, server 2 also uses its local buffer to access its data when it next reads the SCHAR table.
The next three time points of the buffer synchronization process are as follows. Time point 5. A program on server 1 deletes records from the SCHAR table and updates the database. Time point 6. Server 1 writes an entry in the synchronization table. Time point 7. Server 1 updates its local buffer. The next time point of the buffer synchronization process is as follows. Time point 8. A program on server 2 accesses the deleted records. Since the SCHAR table resides in its local buffer, the access uses this local buffer. Therefore, server 2 finds the records although they no longer exist in the database table. If the same access were made from an application program to server 1, this program would recognize that the records no longer exist. At this time, the behavior of an application program depends on the server on which it is running.
The next 2 time points of the buffer synchronization process are as follows. Time point 9. The buffer synchronization refresh interval, as defined in the system profile, has elapsed. Both servers look in the synchronization table to see if another server has modified one of the tables in its local buffer in the meantime. Time point 10. Server 2 finds that the SCHAR table has been modified by server 1 in the meantime. Server 2 therefore invalidates the table in its local buffer. The next access from server 2 to data in the SCHAR table therefore uses the database. Server 1 does not have to invalidate the table in its buffer as it is the only changer of the SCHAR table itself. Server 1 therefore uses its local buffer again the next time it accesses records in the SCHAR table. The last 2 time points of the buffer synchronization process are as follows. Time point 11. Server 2 again accesses records in the SCHAR table. Since SCHAR is invalidated in the local buffer of server 2, the access uses the database. Time point 12. The table is reloaded into the local buffer of server 2. The information regarding the SCHAR table is now inconsistent again on the servers and the database.
Advantages and disadvantages of buffer synchronization are as follows.
You should use the decision-making tree for buffering tables to help you in your development system.